cosmic phenomenon predicted by physics genius Albert Einstein could reshape humanity's understanding of the universe. This process could also help uncover an entirely new class of ultralight particles and provide direct information about the mass as well as the state of gravitational atomic clouds. On February 11, 2016, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, announced a groundbreaking discovery. For the first time, scientists have announced the discovery of gravitational waves. According to predictions in Einstein's general theory of relativity, these waves form when massive objects merge together, creating observable ripples in spacetime. Since then, astrophysicists have proposed countless different hypotheses. Gravitational waves can be used to study physics beyond the standard models of gravity and particle physics. At the same time, expanding humanity's understanding of the vast universe. So far, scientists have proposed using gravitational waves as a tool to study dark matter, or the mysteries within the core of a brown dwarf, supernova explosions, or the merging process of supermassive black holes, etc. A team of physicists from the University of Amsterdam and Harvard University recently conducted a new study. Researchers have proposed using gravitational waves as a method to explore sonar models. One of the two types of ultralight fundamental particles found in nature, often appearing around rotating black holes. This method not only proposes a new approach to distinguishing the characteristics of binary black holes. At the same time, it could also open up the possibility of detecting new particles beyond the standard model. Researchers at the Amsterdam Institute for Particle Astrophysics and Gravitational Physics have continued this study. At National Taipei University and Harvard University, the research findings were published in a paper titled, "The Faint Signals of the Vermilion-Hued Cloud in the Binary Inspirer Lamp Cavity." This research has been published in the journal Physical Review Letters. A common fact is that ordinary matter will gradually be drawn into black holes over time. This phenomenon will form an accretion disk around its outer surface, also known as the event horizon. This disk will be accelerated to an incredible speed, causing the internal matter to be heated to an extreme degree and emitting a massive burst of radiation. Meanwhile, dust slowly settled on the surface of the lamp. However, in recent decades, scientists have observed a phenomenon where the light holes will lose a portion of their mass through a process called superradiance. This phenomenon was studied by Stephen Hawking. That person described how the rotating light holes emit radiation in reality. Those who stand close see clearly, while those far away see only a blur. When transforming radiation from one reference frame to another, the outer shell of the seed is what enables it to transition from a virtual state to a real one. This strange type of energy, called Hawking radiation, the lighter particles will cluster together, forming clouds around the black hole. This causes the atom to be attracted by the gravitational force of the throne. They are named as such due to their shape resembling that of ordinary atoms within the particle clouds surrounding the core. While scientists have confirmed the existence of this phenomenon, they also realized that it could only be explained thanks to the emergence of a new ultra-sensitive particle existing outside the conventional mold. This is the core of the new article, the main content will focus on. The lead author is Daniel Baumann, an expert in particle physics and gravitational astrophysics. Amsterdam and his colleagues at Taipei University check the mechanism of unstable ultralight boson cloud formation caused by ultrasonic waves. A natural formation often occurs around black holes. Additionally, they observed similarities in the gravitational forces between atoms. And if we delve deeper into the structure of an ordinary atom, in short, they concluded that it was a binary black hole. Can make the particles in their cloud more stable. Through the photoelectric effect, light can be converted into electrical energy. As Amstead pointed out, this phenomenon occurs when the electron's energy, for example, when light shines on a material, make it emit light through excitation, also known as the photoelectric effect. When applied to a binary black hole system, Bowman and his colleagues pointed out that the ultra-light, floating clouds can absorb energy from orbit of a companion stepping into a black hole. Some motherboards will be pushed out faster thanks to this. Finally, they succeeded in proving this process. This could significantly impact the evolution of binary black hole systems. As mentioned, orbital energy was lost in this process. it is possible to compensate for the damage caused by radiation from the Milky Way. It was gravitational waves, so the ionization process drove the development. It's not just about causing disruption. We demonstrate that ionization energy exhibits distinct characteristics, leading to a development process that is not linear but full of unexpected twists and turns. Of the frequency emitted by gravitation or wave, they believe these zigzag lines. For next-generation gravitational wave interferometers, this will be easily detectable. The name of the interferometer space is Galissa. This process can be applied to explore a completely new type of ultra-sensitive particle and provide accurate information about the volume and the state of gravitationally bound atomic clouds. In summary, research on gravitational waves continues to advance relentlessly. Use more sensitive interferometers may reveal strange physical phenomena, contributing to enhancing humanity's understanding of black holes in the universe, and opens up groundbreaking advancements in the field of particle physics. In the future, astrophysicists hope to apply these tools to their research. Like black holes and neutron stars, they also expect that these primordial gravitational waves will help unravel the mysteries of the early universe. Revealing the mysteries of the universe's earliest days, help unravel the mystery of the matter-antimatter imbalance, and pave the way for a new quantum theory of gravity. So what do we truly expect from quantum gravity theory? A hypothesis on quantum gravity helps us understand how quantum matter interacts with gravity, especially when gravity becomes extremely strong. With gravity weak enough, we can fully achieve quantization, just as we quantize other interactions. But quantizing in a weak gravitational field was no longer important at this point. When gravity reaches high intensity, such as in the case of high-energy particles, and collide with each other at extremely high energy levels, the particles themselves inherently possess a strong attractive interaction. Quantum gravity could also reveal to us a phenomenon that occurred in the universe during its earliest period. According to the general theory of relativity, our universe originated from a singularity. This absurd result only proves one thing: we need a clearer explanation. The more fundamental nature of space and time at that moment, because the gravitational force in the early universe was extremely strong. Therefore, the quantum effects of gravity cannot be overlooked. When describing this stage of the universe, general relativity also predicts the emergence of singularities when matter is compressed to an extreme limit. When matter is compressed strongly enough, it forms black holes, leading to a phenomenon known as the black hole information paradox. The fact is that black holes emit thermal radiation due to quantum effects, not accounting for gravitational effects within the quantum realm. But when the black hole completely evaporates, the only thing left is thermal radiation. It's unclear what created that black hole. The information will be lost in this irreversible process. But since irreversible processes cannot occur in quantum mechanics, as we know, this creates a contradiction. Quantum gravity will help explain what happens to the information inside a black hole. When solving these final difficult problems, the theory of quantum gravity will achieve success. At the same time, it must also be capable of reproducing all the results of general relativity. And this is the standard model in the field of fundamental particle physics. And it must make verifiable predictions.